All right, we want to look at solving quadratic inequalities in one variable, and this topic really involves you applying your understanding of a number of different concepts. So I'm going to begin with just looking at a quadratic function, which, remember, the graph of that is always a parabola. The leading coefficient's positive, so when we know it opens up. This number here is -3, so when x is 0, y is -3. That would be the y-intercept. We could factor this expression and write our function like so. And that would be handy because that would give us, if y was 0, the x-intercepts at 3 and -1. And so what I have over here on the right is a graph of the function. Now just remember what a function is. A function means each x has one y. And in a relation, we can put a value of x in and label what comes out the value of y. So there's an infinite number of values of x we can put in, and when we do that, we get an infinite number of values of y, which produces the graph. So I've got a quadratic function. All right, so now I'm going to change this expression, and I'm going to make y 0. And this is what we call a quadratic equation. The difference now is that there is only one or two values of x that will make the y value 0. So what we are now saying is that the output for my y must be 0. But there is a connection between the equation and the function, as we know, and as we've talked about before. When y is equal to 0, the x-intercepts on the graph give us the solutions to this equation. All right? So we know the solutions are where the graph intersects the x-axis, which is at x equals -1 and 3. Okay? We can also solve the equation algebraically by factoring, setting each factor to 0, and then coming up with our roots. Alright, so these are concepts that we've talked about before. So now what we're going to do is we're going to extend this to what would it mean if I had an inequality sign in this position, a less than, for example. Well, again, there's a connection back to our function. If the zeros of the function are when the equation is equal to 0, then it stands to reason that when the function is greater than or less than 0 must happen at some other values of x. Now what we can do is we can think of this as our function, the y values of our function, and what we're saying by this expression is that the y values of our expression are bigger than, the right side is the bigger side of the equation, are bigger than 0. Which values of x make the y values of the graph bigger than 0? Well, that would be the values of x where the function is above the x-axis. So for example, on my function at -2, an x value of -2 will have a y value, which is the calculation of all this, which is positive. So we say that the solutions to this inequality in one variable are the values of x where the graph is above the x-axis, which in this case, let's just show this on a number line, and let's just superimpose our graph on top of it. When the function was equal to 0, those were the zeros. Well, the function isn't equal to 0 because there's no equal sign, so we don't want to include these 2 points, so I'm going to use open circles to show that those are not part of the solution. But values of x that make this positive are in this range and this range. And so therefore x is less than -1 or x is greater than 3. In the last example, I solved it through a combination of algebraic and graphical means. With this example, I'm going to do the same thing, but I'm going to focus more on the algebraic way to approach it, and then bring in the graphical parts of it later. So which values of x make the left side smaller than the right side? I'm going to begin here by multiplying both sides by -1, just to get that negative off the leading coefficient. It's easier to work with. Now, I just want to remind you that whenever you multiply or divide both sides of an inequality by a negative, remember that the sign switches. Okay, that goes back a few years. We talked about this. For example, if you had 3 is less than 5, we know that's true. But if I multiplied both sides by -1, the opposite side now becomes larger, so the sign switches. All right, so just be mindful of that. If you happen to multiply or divide either side by a negative, the inequality sign will switch. All right, so the first thing I need to do is I need to find the values of x that make this equal to 0. Because the values of x that make it more than 0 are in other places than when it is 0. When the function is 0, that's kind of the transition point between where it's less than or greater than. So first, I'm going to find where the expression is equal to 0. And that happens if I factor this. That happens at x equals 5 or negative 2. And so I'm looking for values of x, so I'm going to show these on a number line. And these values, when plugged in, make this thing equal to 0. We don't want this equation to be equal to 0. So these are not part of our solution, so we put an open circle. Remember, something that's an open or a dashed or not colored in means it's not part of the solution I'm looking for. Which means that the solutions must be somewhere else, specifically in one of these three regions. So in the last example, we used a graph to decide which intervals we would select. This time I'm going to use test points in each of these intervals to see which section works. So what I'm going to do is I'm going to test a number less than negative 2, so let's just pick one, negative 3, and I'm going to substitute that back into my original statement. Now, I could use either of the two expressions. I'm going to use this one. Okay, so I'm going to use this as my original expression. Doesn't really matter. Okay, so we're going to have negative 3 squared minus 3 times negative 3 minus 10. Is that greater than 0? So 9 plus 9 minus 10, it would be 18 minus 10 equals 8 is greater than 0, which is true. So x equals negative 3 is part of the solution, as will be any other value of x in this section, so I shade it. If negative 3 is producing a number that works, anything else in that interval will also, because the zeros of the function are where we translate between greater than and less than. If I plug a number in between negative 2 and 5, let's just pick one. Nice easy one would be x equals 0. Let's plug it back into my starting statement, which I'm using as this. 0 squared minus 3 times 0 minus 10. Is that greater than 0? 0 minus 10 greater than 0. Is negative 10 greater than 0? No, it's not. It's false. We don't. That doesn't satisfy the inequation, so we don't shade the middle section. And finally, we pick a number greater than 5, so let's choose 6. Back into my original statement. 6 squared minus 3 times 6 minus 10. Question mark. Is that greater than 0? 36 minus 18 is 18. Minus 10 is 8. Is 8 greater than 0? It is, so I shade the numbers in that section. Okay, so I've highlighted the numbers that make this inequation true. If I want to do this in a more graphical way, what I can do, I can look back at my original. Again, remember I'm using this as my original now. And I say this is my function. Think of this as a quadratic graph, quadratic function, y1. And what you would be looking for is where your graph of y1, which you know is a parabola opening up, which values of x make the y values positive? Well, if you just think about that, when the y values in a graph are positive, that is where the graph is above the x-axis. So we could write the solutions are the x values where the graph is, in this case, above the x-axis. Okay, and then instead of showing all this substitution and interval checking work, you could just sketch the graph in on top of the number line. Okay, so I'm going to superimpose my parabola. The negative 2 and the 5 are the zeros of the function. So, and since I know the graph opens up, I know that the parabola would look something like that. And which values of x are where the graph is above? Well, the graph is above less than negative 2. or more than 5. Okay, in the end, you need to state the solution sets. X is less than negative 2, or X is greater than 5. Alright, so the first two methods I showed you for solving quadratic inequalities was a combination of algebraic and graphical approaches. I'm now going to show you a third method called sign analysis. So, same question as before. I'm going to begin by multiplying both sides by -1 just to move so that we have a leading coefficient of positive. That switches the sign. Alright. So the way this method works is I leave the inequality where it is. I factor my expression, assuming you're able to factor it as you are here. And then what we're going to do is we're going to look at each of the factors separately. Okay? So we're going to look just at x minus 5. And we're going to look at where x minus 5 is positive or negative. Okay? So I'm going to draw a number line here. And x minus 5 would equal 0 when x is 5, wouldn't it? And if we put a number in bigger than 5, like 6, 6 minus 5 would make the numbers along here positive. Would make the outputs positive. And values of x less than 5 would make the outputs negative. Okay? So now I'm going to look at x plus 2 just by itself on its own number line. So where is x plus 2 positive and negative? Well, first of all, let's consider where it's 0. This would be 0 if x was negative 2. Now, by the way, I'm just lining this up so that negative 2 would be there still and 5 would be here. Okay? Now, if we put a number in bigger than negative 2, like negative 1 or 0 or 1, the output to this would be positive. And less than negative 2, the output would be negative. Okay? So we've looked at the case of this factor, we've looked at the case for this factor, and now, you might be seeing where I'm going with this, we're going to look at the case for the two together. Where is x minus 5 and x plus 2 positive? So let's draw a third number line, and we're going to put the sort of major reference points from above down here. Negative 2 and 5. And the whole concept we're using here is that something times something has to be, this whole left side has to end up being bigger than 0, positive. And so we know a positive times a positive is positive, or a negative times a negative is positive. And since we know where each of these two factors are positive and negative, so for example, less than negative 2, this is negative, x plus 2 is negative, so negative times negative will make this section positive. Between negative 2 and 5, we'd have a negative value here times a positive value here to give an overall negative value between the two. And then we'd have positive times positive to give us positive. And then finally, you should consider what is going on at the boundary points. Since a value of x equals negative 2 and 5 produced an output of 0, we know that 0 times anything will make the new value 0 on the combined expression. And so, putting it all together, what we want is we want to identify the values of x where our expression is greater than 0, in other words positive. Not including 0, so we will not include negative 2 and 5, open circles, and we will shade in the regions where my output is positive. So x is less than negative 2, or x is greater than 5.